Welcome to my project showcase. Its name is Finder Drone. It's an AI-powered drone that finds pets, people, or whatever. Okay, the motivation for this. Um, okay, the motivation for this project came from something that happened to someone close to me in real life. A couple years ago, she lost her cat, and um, and well, it was very difficult to search it and trying to find it. So I borrowed a drone from a friend, and we tried to record an aerial view of all the surrounding sounds from the house of the cat, and recording video, and then we looked in the video and searched the cat manually. Unfortunately, the cat wasn't found ever, but well, that idea was an inspiration for this. When the project showcase challenge was announced, I said, "Oh, it would be so cool to do that, to program an intelligent drone that would search for something lost automatically." And I said, okay, if I get a drone, I'm going to do it. And so I was able to get a drone, and I did it. Okay, and this has many appliances. It's not just to find cats or pets. This could serve for example, for rescuing people on disasters, or for anything. It has many appliances with the same core idea. Okay, the objectives for this project are to program an autonomous drone that finds and tracks a specific subject from aerial images in real time. So that a drone captures aerial images like this. Well, this is from a professional drone, not the one I get, but and here you can search for many things. Okay, but the project, the use case for this project will be to find a specific cat or any cat based on a video of it. So you can record a video of your cat, and the drone should find it. Okay, with some restrictions, of course. Okay, then the project must be extensible to find people or other kinds of subjects. Okay, so yes, this core idea, well, in the project has to be extensible. So if we change the detector by a different model, it should be easy to, for example, to change it to person finder model, and it should work. Okay, also one objective is to use the techniques learned in the course, and one more objective is to achieve a working demo, not theoretical. We wanted to do a demo with a real drone and all that, and not just a theoretical work. Okay. The project scope. Okay, the project will run with a small, non-industrial drone. It's a DJI Telodrone. It's a very small drone, as you can see in this image. And it's a very simple drone. It doesn't offer much, so that limits in many things. But it doesn't affect the core idea. Okay, then the project will run detecting toy and real cats from aerial view. Okay, so with toy cats, because well, they're easier to handle, and you'll see why. and also real cats. I want to detect also real cats. Okay, then it will run on a small delimited area. Drone will fly around 2 meters high. Okay, due to the limitations of the drone and the scope of the project, and well, and the time for it was basically 2 weeks. It's going to be in a small area, and not very high. Okay. It will find any cat or a specific cat based on a video feed or a set of pictures. Okay, as I said, you'll be able to record a video of your cat, and then the drone has to find it. Okay, then the training will be done in a federated way using Raspberry Pis. Okay, so I wanted that all the training to be on Raspberry Pis. Okay, so the basic idea is, okay, let's say that this grid is all the field where you want to search for the cat, and we have well, here a ball, a green cat, and a blue cat. Let's say we want to find the blue cat. So the basic idea initially was to fly in a spiral. Then this ball, for example, would be ignored. Then this cat would also be ignored because it's a green one and we don't want him. And then until he finds the blue cat. Okay. Why in a spiral? Because let's say you lose your cat from your house, so that most probably it will be close to the house, right? So we have to search there first. Radially, and so that's why spiral was my initial choice. And yeah, it's basically that. Well, it was, and so it sounded very easy. To be honest, I said, okay, let's say I have let's say I develop a good classifier. So it will be very easy, just flying the drone until it finds it and stops, and that's it. I said, okay, this can be done in a weekend. But that was in theory. I was so wrong, so wrong. The effort it took was, I would say, 10% on the theoretical idea and 90% of implementing it for real. It's very different to think something in theory in your mind and say, oh, okay, yeah, this can be easy, and to implementing it, there's a big gap there. Okay, yeah, so that's the basic idea. Okay, and now if we see it in a more 3D view, okay, here we would have the drone in a field, and well, finally I didn't do it in a spiral, as we said, because there were some drone limitations. I will explain later, and so this would be the idea that the drone will go flying until he finds the subject, and there can be other objects. Or whatever in the middle, but they have to be ignored until finding the target. Okay, so like this. So in this case, it found the cat, but it doesn't have to only find the quadrant. This is what the drone sees. Because let's say you have an aerial image with, I don't know, like the one I showed initially, like this. So it's not useful if the drone says, okay, I found a cat in this image. It's not useful. You have to determine exactly where. Okay, so that's also important. So like this, right? So okay. So that's an overview of the project. It looks simple, but believe me, this became so hard. Well, this project will have basically 3 modules. One is the object detector. This means that we have to find the coordinates of where a cat is, or where any cat can be in an image. And regardless of which cat it is, it's just finding the coordinates of the cats in an image. That's the object detector. Then we have the drone autonomous flying. That is, well, that the drone has to fly in a pre-programmed path that we are going to call mission. And the last one is the cat classifier that we are going to use to detect which cat was found. Okay, so for example, I want to search this cat that I'm going to introduce later. So there has to be some kind of classifier, so that if I find this cat, this has to be ignored because it's not the cat I want to find. So here comes the classifier that will be trained in Raspberry Pis. So the first component is the object detector. This detects the coordinates of any cat found on an image. So in this case, it would give us the coordinates of this, this rectangle, this box, of where any cat is found with certain probability. And for this, I used the faster RCNN object detector model. And based on it, I created a faster RCNN flipped model that is suitable for aerial images, well, more suitable than the default one, because faster RCNN is, well, it's trained with images from the front, right? So this cat is from the front, so this is detected by faster RCNN, but with defaults. But let's assume that this image is flipped vertically, because the drone could catch it that way, right? So by default, the faster RCNN wouldn't work. So I had to modify it to consider also the vertical flipping. Yeah. Horizontally, there isn't any issue because it doesn't matter if it's flipped to the left or right. There's no problem with that. But vertically, that's an issue. So to test the detection model, well, first let me run this test detector frame. It was one utility file I had. Usually I put in the instructions to the top. Okay, and we are going to run over an image and to detect the coordinates of the box, right? Okay, it's loading the model, and here it is. So it detected a cat here, okay, and with the coordinates. Okay, now let's see how that was done, but very briefly. Cat detection model inherits from faster RCNN flip detection model, which in turn that inherits from faster RCNN detection model. Okay, so that there's a class hierarchy. Speaking about this, this is because, well, I did a small framework for my study group for all these kind of object detection and class, for object detection, basically for faces and all that. Well, that's another subject, but I used that framework as a base for my project. So that's why you say what you see here: face detection model. There's YOLO, SSD. Well, many things. Okay, let's go to the core. Okay, so here in the faster RCNN flip detection model, we are basically using it's a faster RCNN, which is an object detector. As I said, it detects objects in images and tells you what it found. I don't know, I found a cat, I found I don't know, a ball, I found a shoe, and all that. And I chose this because well, this has good CUDA support, and I was able to run it with PyTorch without problems. And yeah, I really needed good performance because well, when the drone is flying, I need to have a good frames per second rate. So okay, that's why I use faster RCNN. Okay, so okay, so what we are doing in the flipped one is it's what modifications it has from the original one. Okay, first one thing is I am initially you could think of the following. Yeah, let me show some images where it is. Okay, here, for example, let's consider this image. Okay, so this is an image captured by the drone. Okay, that doesn't matter. Okay, so we can have a okay, so if the image is like this, faster RCNN won't have any problem. It will detect a cat, and I don't know, well, okay, it will detect a cat, okay? But if it's flipped vertically, we might have problems because faster RCNN won't detect it, okay? So let me show you an example. So something like this might happen, okay? So it wasn't detected. It detected this as I don't know what object, it doesn't matter, but it didn't detect the cat because the model is trained with images from the front. So it can work with images from above, but as long as they are not they are not very clearly flipped like this. So this won't be detected as a cat. Okay, so one option we could do is, well, we can flip the image and well, as this. So we could try with both flips, right? Flipped and unflipped. And but that also has a problem. Okay, so okay, if we flip the image, we get this, and we have the detection correctly. And we could say, okay, it's just a matter of having the two images, flipped and not flipped, and run the object detector twice, and that's it. But there are two problems with that. One is running the detector twice is expensive. Because when I will be flying the drone, every frame per second is very precious. So if I'm running something twice, it's twice the time, and remember that it's not only detecting the object, then we are going to run the classifier as well, right, to determine which cat it is. So it's doubling all the times if we do just that simple approach. And the other problem would be that, let's say this is detected as a cat like this, but if I flip the image, it's detected, I don't know, as a horse, let's say. So I would have two detections for the same area, and which one I'm going to choose. Yeah. So for that I'll explain the approach, and we are solving that with non-maxima suppression. Okay. Let me go back to the code. Okay. Okay. So here in the faster RCNN. Sorry, I'm extending too much. Okay, let's go to the core. Okay, so I'm doing two things. I research and this faster RCNN supports sending an array of images that will be processed in parallel, and this is exactly what I needed. So I'm flipping the original image, and I'm sending the original and the vertical flipped one, and both will be processed in parallel with CUDA. So it won't add to my processing time, fortunately. And I had to do this and then applying the non-maxima suppression, which is here, which I found, fortunately, Torch Vision had it already. And non-maxima suppression, so we fix the horse or cat problem here. Yeah, but it's basically that. Then the rest of the code is trivial. Yeah. And that's it. All these models inherit from base detection model. So, well, this is a little off topic, but So you could switch the cat detection model by I don't know, person detection model if it inherits from this class, and all the code will work. So instead of having a cat finder, you will have a person finder, or you can have a horse finder, or a ball finder, or whatever. So this is part of the small framework, and yeah, we have many models here. Okay. Oh, I extended again. Okay, let's continue. Okay, so the cat detector is done. We were able to solve the issue with faster RCNN flipping, and we can detect cats. Okay, well, one thing to note here is, well, we are using the faster RCNN as a base, and we are filtering for the cat category to find the cats. And one reason, well, some of you might be asking, why didn't we customize that model to directly find the specific cats? And that has a reason. That was possible to do. Actually, I did my own object detector. You can check a sliding window.py. That well, as the name says, it was using a sliding window approach, which is an approach of computer vision. But the problem is that it needs two problems. One is it needs a really good classifier of things you want to search and things you don't want to search. Well, I want to extend on that. And the other is that that operation was going to be, that training was going to be very expensive. And well, one of my objectives was to use Raspberry Pis. And well, it would have been too much for the Raspberry Pis. So that's what I split it into. First, use an object detector, like faster RCNN, and then the classifier separator. Okay. Okay. So okay, cat detector is done, and now let's see the drone. Dun dun dun. Okay, I thought this was going to be the easiest part, but it was the hardest. Okay, so for the drone and autonomous flying, well, the drone has to fly based on a program path. It could be, I don't know, a spiral or scanning sequentially, but also it has to, of course, it has to be smart to find cats using the cat detector, and later also the cat classifier. So it has to be a smart autonomous drone. Okay, but there was one issue. Well, many terrible issues. I will show you. And okay, I'm going to show an unboxing video. You can skip it if you want. And I got a surprise when I received the drone. I was very disappointed. Okay, let's see it. Okay, the drone just arrived. I'm excited. I was waiting for it. I realized on Saturday that the challenge will be for 20th. So I needed desperate. Hola, ¿qué tal? Buen día. Claro que sí. Pucha, qué bien, estaba esperando harto este paquete. Okay, let's open this thing. I received it from Santa Cruz, which is another city here in my country, in Bolivia. And yeah. Oops.
awesome. Can't wait to program it. Here, camera. Oh no. The camera is in the front. Oh my god. I thought it was downwards.
So as you saw, sadly there was a big surprise that the drone's camera, it's actually in the front, pointing forward, and what I needed is to aerial view, so for the camera to be to the bottom. This was disappointing. I should have researched better, and yeah, I was sad because everything I coded was assuming that the camera would be to the bottom. I don't know why. I thought it would be, I don't know, that you were able to adjust the camera or to be to the bottom by default, but it wasn't. That was my bad. And well, this is I expected maybe too much for this drone, and there wasn't time to get a new drone. There was well, too little time left, and also it would have taken time, money, and all that. So I was thinking to well, if I didn't get a solution, I would have have needed to change my project to do a different thing and all that, and that's that. So well, I said, okay, I have to solve it, and one idea that I had is to place a mirror to 45 degrees here, so it would reflect what's the floor. And okay, so okay, I said I have to try it, and I got an idea of using a dentist mirror to reflect the image. And yeah, so I asked a friend who's dentist to give me one of these, and yeah, and it well, it kind of worked. Well, let me show you. Okay, so this is what I did. This is the dentist mirror, and I place it. Well, I removed the drone cover and placed it with elastic bands and some cardboard. And here's another view, and surprisingly it worked. I was very happy. Well, I had to calibrate the angle to be 45 exactly. I had also to bend it. It was plastic, and yeah, because it had to be something light, because it affects the drone. Okay, so yeah, after a couple hours, I was able to have the correct angle, and it also flipped the image, so I had to digitally flip it over vertically. That was easy, and yeah, so I was really happy. I tested it, and I was able to get the aerial view I wanted. Fortunately, that I was very happy. Yeah, because if not, my last, yeah, I would have to rethink the project or do something theoretical, and that's the last thing I wanted. Okay, so I had the area view. I was happy, but that wasn't the last issue with the draw. It was just beginning. Okay, so there was one more problem. The erratic flight. Okay, so the drone, when you control it manually, there's no problem. There's no problem, because well, when you are controlling it with the control or with the cell phone app, it obeys you, and yeah, and basically it works fine because you are seeing the drone. So you say, okay, go more to the left or more to the right or more forward, backward, and given you're seeing the drone or you're moving your finger while seeing the drone, it works perfectly. But it's a very different thing when you try to program it. Okay, so I use the I read the official SDK for this, and used a wrapper done by Dania Fuentes, a wrapper that makes it easier to code with Python. And yeah, so okay, so initially yeah, I thought, okay, this is going to be easy. I'm going to say, okay, go 1 meter forward, 1 meter to the left, and I could do the spiral. But in reality, no, it was very different. So let's say okay, a program, okay, drone go 1 meter above, oh sorry, forward. So it sometimes did, I don't know, 1.3 meters, or other times 0.8, and it was very erratic. So the attempt of the spiral was like this. Well, this is exaggerated for you to get an idea, but it was something like this. So it wasn't reliable at all. I also tried to do the sequential scanning, and yeah, the same problem. Sometimes it was, the distances were shorter, sometimes larger, and I had it in both cases crashing to the walls, and yeah, that was okay. So it was one more disappointment of this. And I also tried, instead of telling it to fly a certain distance, I tried with the speed, to set the speed and control the time, but the speed was also erratic, so it was the same problem. And yeah, I said, okay, how can I solve this? If you think for a moment, it's kind of hard if distances and speeds are not accurate. So I said, okay, the drone sees well, okay, and so a little parenthesis here. The drawback of putting a mirror to the drone was that the image quality dropped. It was inferior than without the mirror. So yeah, but there was no other choice. So okay, closing the parentheses. Okay, so but the drone in general terms sees well. So I said, okay, I have to. That's my only choice is to use its sight to improve the movement. So I had an idea to place some visual breaks. Okay, so if the drone sees a break, it won't go beyond. Okay, so this would be the objective. Okay, we would like, in a sequential flight, to do it like this, right? So I had the idea to have these breaks, these visual breaks, and so I tried it with wooden pieces, square wooden pieces, and so to place them here, and I did this. Okay, so I placed these squares, wooden squares, as breaks, so that the drone could, if it sees a square, it won't go beyond. So in the queue that it has, because I programmed a queue of operations that the drone will follow. So if for example, he's flying like this, and he finds a break, and he has more forward steps in the queue, they will be discarded. So the next one will be to the left, and it will go like that. So these are protecting the forward, this backward, and this to the left, and I also had to the right. And yeah, this was a good idea, but it introduced one more challenge for the drone to detect these squares. And yeah, and even this wasn't enough. Okay, so let me show you a little this idea a little more in detail. Okay, so I made this square wooden pieces with electrical tape in the borders so that it will be easier to detect. And this was the idea. Okay, I had this threshold rectangle, and I said, okay, if I have a square to the top, it means I have to stop, right? Going forward. If I have a square to the bottom, I will have to, well, not go backwards more, right? Same to the left and same to the right. Okay, and everything was based on the center of the square. Yeah, I had to do a square detector, and yeah, I'll talk about that later. Okay, and okay, so here I had some coordinates, and yeah, this seemed that it was going to work, but unfortunately there was one issue. The drone doesn't stream on real time. Well, it does, but for this project, I wasn't able to to stream and process in real time, because imagine in each frame we have to do object detection and object classifying, and also, well, stream the image and move the drone. There are many things that are happening at once, so we cannot operate at, I don't know, 20 frames per second. That would be insane. So well, by the drone, well, by the estimates of the neural network running of the object detector and all that, it should run at 2 or 3 frames per second, not more. So and add to that, you can add there's a small delay between what's happening and what you get in the computer, right? So unfortunately this didn't work, because the following happened. In theory this was awesome, but in practice something like this happened. Imagine that the drone is going forward, okay, like this, but for some delays and processing times and all that, you get this frame, okay, so a little too late. It's assume that it's the same as this, but a little later. So the drone went forward and it's a little later. So when the drone receives this, he will say, okay, these are to the bottom. I don't have to stop going forward, and it will still go forward and crash to the wall. And even worse, this might become brakes to go backwards, right? Because they are now backwards. Well, they fell behind the drone, so it's like crossing a country border and not being able to come back, right? Something similar. If for some reason you lost that frame, then you cannot go back. So the drone cannot enter the wanted area again. So it was the counter effect. And yeah, this was also, well, not expected, but these are the things that happen when you do it in reality and not theoretically. So okay, so I had to rethink this solution. Then I said, okay, what if we can put a direction to these squares, so that I could say, okay, this square should push you to the bottom, right? Should not allow you to go forward, but to push you to the bottom, right? So this would solve the issue. Let's say this square has some indication that it has to push to the bottom, and we have it here. This rectangle won't be used anymore, and it will tell me, okay, push back, and I don't care where he saw it, where the drone saw it, sorry. And yeah, so this is the next solution. So I put this like a mustache in one direction. For example, this piece of wood will push the drone backwards, and this will push the drone to the right. Okay, and to achieve this, I also had to detect this small mustache. And okay, so okay, let me explain a little about that. Yeah, I used OpenCV and detecting contours first to detect the squares, and then also, yeah, I tried to use the to detect the darkest spots, but that wasn't working. So I inside the square, I detected another shape, right, another polygon, and internally it uses convex hubbles and many things. And this was the result. So first, well, it has to detect the square, and it has to transform it because it's in perspective, right? This will not always be flat and a perfect square. So it has to do some transformations to become perfect squares, and then detect these spots. And due to this is taken with the cell phone, but this is taken with the drone, so the shapes are not exact. And this is the output of a small program I did. This is not addition. So it's with red, it's detecting the shape, and it's well, putting a circle. So this gave me the direction, right? With these coordinates, I was easily able to say this is to the right and this is down, right? Okay, and if you want to see the code about that, let me show it very briefly. It's here in utils, square utils, and it does many things here. That most of this was inspired by image search blog, which is an awesome resource. So okay, it's here. It's doing all that, and okay, if you wanna take a look, okay. Oh, sorry. Where am I? Okay, so okay, so what I did is add this to the project output, and this is the final result. So you are going to see it in the project output. Well, this is a rotated image for demonstration purposes, but it's going to detect and draw a square, and then a cross, and based on where it found the mustache, it will put a blue circle indicating the direction. So in this example, this would be telling you, okay, go right. And this, well, this wasn't detected properly, one of the earlier versions. And well, a blue circle should appear here, and it tells you, okay, go to the bottom, and this will tell you go to the left, to the right, sorry. So with these pushers or brakes or whatever, more appropriate they should be pushers, because it will push to the right, and it will push to the bottom. So it will create a vector, a diagonal vector, and will send the speeds to the drone to bottom and right, so it would be a diagonal. So it will push the drone. This case will push the drone in diagonal. This will happen only in corners. Usually you will have only one of these to push in one direction. And okay, so this was more work, unexpected. But looked at the drone is becoming smarter than we thought because it's detecting all this. And one more thing is I used well, conventional approaches to solve this, and not deep learning, because this would have been overkill to use deep learning to detect these squares. This would have taken more time. That's less frames per second and sluggish drone, and well, it wouldn't have worked. So why using deep learning when you can solve it in an easier way, right? Okay, and so it's been a long, and I even haven't shown you the drone flying. So let's see this approach, how it works. in a demo live. One thing I forgot to add, when in the live demo you're going to see, well, the drone is flying. Well, I programmed it to fly in random directions, and the idea is that it doesn't have to go out from the area delimited by these squares. So that's, and also there was a take one that failed. Unfortunately, I don't have that video. I don't know what happened, and so I'm going to show you the take two that worked. And okay, let's see it. Take two. Okay, so the previous one failed because there was a division by 0, calculating the convex hull. Now it's controlled, and let's see how it goes. Let's go drone. Okay. Okay, let's see. Okay, that's going well. Didn't went out. Oh, that's cool as well. Yeah, but that's fine. That's fine. That's fine. Don't go out. Don't go out. Yeah. Awesome. 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 No, 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 no. Yes, please. It's going well. Yeah. Yes. Come on, come on. Come on. Come on. Let's see the output here meanwhile. Keep detecting the squares. Okay, it's going very well. Didn't come out. Wait. Yeah. Let's go. It finished. It finished. It finished. Yeah. Yeah. Great. Awesome. Okay. One thing I didn't show you is the code for the drone. Okay. Here we have this main.py file, and okay, I won't explain it in. I extend too much. Sorry. So I will try to be brief on this. Okay, there are some arguments. The first, well, one of the most important is the mission. So here I tell the route for the drone. Okay, so in this case, I don't know, it's go 7 steps forward, 1 pause left, then pause, then backwards, and then left, and this 10 times. There are other parameters, and so the mission is the, well, what the drone will try to accomplish. Then we have some modes, non, find, follow, flip. Yeah, they are self-explanatory, and we connect to the drone API, the Dania Fuentes API in Portello, and I also used some. I forgot his name. Sorry. Okay, so okay, so it's an infinite loop that it's running. So we get each frame, and we are not using distances or anything. We are just setting the speeds of the drone, of each of the motors, to the top, to forward, backward, left, and right. And also we have here the frames per second. That this comes from a calculation based on the neural network and all that. It can be 2 or 3. Okay, and then we have here we take off the drone. Okay, and we have also some manual controllers just in case, so that we can also control the drone manually if there's an override flag, if that's turned on, and you will see it in the screen when it's on manual control. Okay, and it's the keys. And when I'm with Autopilot, which is the default mode, it will build from the mission. It will do it will produce a queue of operations, and that's like simulating the keys that would be pressed if you would be doing this manually. Okay, and there's a queue and all that. Okay, and okay, all this if he finds the well, we are going to see this later. And okay, so it's basically that, and here's the square detection. Okay, it's detecting the squares, and based on and this is pushing, right? So if it finds a forward a square to the forward, it will set the velocity to a positive number, and then backwards to a negative number, and all this, and it operates on the queue, and well, many things. Okay, and these are the detections. We don't have that yet in the demo. Okay, so yeah, that's in a nutshell. And as usual, we have the instructions to the top of how to run this. And yes, you need a drone to run this main.py. In a future, I'll try to code a simulator so that anyone can run this code without having an actual drone. But for now, you do need a drone to run this. Okay, that was it. First, let me introduce you to Whisky. This is our toy cat that is going to help us in all the project. And well, so I'm going to place Whisky approximately in some place by here, and I also delimited an area with the wooden pieces. And they have the mustaches as well, as we said, and the drone will do a sequential mission, okay, until he finds Whisky. Hopefully. Okay. Now, well, we didn't explain much about the drone code, but basically, well, it has three modes. Well, more internal modes, but known, find, okay, and found, aka follow. In later, you will see. Okay, so the known state is when you start. Find is the most important one. When the drone is in find mode, it's the autopilot that is is doing the mission, but also doing the AI, right, to detect if there's a cat, and later it will do all the classifier as well. So this find is the core mode of the project. Okay, so the drone will do this mission until he finds a cat. Remember that for now we are just doing a cat detector, but not classifier yet. So it will find any cat, and the only one we are going to place here is Whisky. You might be wondering why Whisky. It's because he likes whiskers. What were you thinking? Okay, and Whisky as well, of course. Okay, and so for this, let me show you a little about the code. Okay, so the drone in the infinite loop, it's getting a frame each time, and okay, and with that frame we're going to trigger the detection. Let me show you. Okay, self.detect subjects. Here it is, and it sends the frame and some other parameters, and that's it. Okay, here we have the sorry for this. Where is it? Okay, detect subjects, and here we are going to all the AI. For now we are just searching for any cat. Okay, and when it finds it should show a window here with well, besides the output window, one more window with the detection, with Whisky's picture, hopefully, at that time. Yeah, it's basically it. Okay, better to show than speaking. Okay, so let me show you that. Okay, so the command we're going to run is this: python main.py --cat any, and mission, it will be this mission. Forward, left, back, left, and just in case put more forwards, so that well, the brakes will work. It's better to have more than to have less and not enough. Okay, let's hit it down. We are running the program, okay, with a sequential mission, and let's see if the drone finds Whisky. Okay, let me put a little more here. Okay, and let's take off. Okay, and start the autopilot. Okay, it's going well. Here you can see the project output, detecting the squares. Awesome. Awesome. Awesome finding. Let me show another perspective. It almost went out. Okay, we found it. We found it. Let me show you. Yeah, it's been found. This is awesome. Okay, success. Okay, that demo worked perfectly. Okay, I'm happy. Okay, now, well, every time the program runs, we create a session, which is basically all the frames captured. And here we can find some interesting things. For example, here, it detected the squares. Well, it detected these, but didn't detect the mustache. Okay, that needs some fine-tuning. Okay, and the drone is in fine mode. This is the autopilot, which is flying autonomously and doing the AI to detect the squares and fly and search for the cat. Okay, we have that. Then what else is interesting? Okay, here is the first frame where he found Whisky. Okay, so he found it here, and it started. Okay, it showed as you saw, it showed a window in the previous video with this picture. Well, surprisingly it found it, even if it's partial. In other tests I did, it had to be the full cat picture. And one, okay, let's see, for example, this. Okay, this as you can see, in all the rest of the frames, Whisky is detected. Okay, so here one thing to notice is that Whisky was found even if he's flipped. Well, that's right. So this is thanks to the flipped faster RCNN model we did. Because with a regular object detection model, maybe this wouldn't have been found because it flipped. So that's a plus. So our flipping detection is working, and yeah, it's basically that. And yeah, and also the frame rate has been calculated and calibrated for all these to work. While calculating the times it takes to detect the squares and the cat and all that, and so the frames, currently we are running at 3 frames per second, if I'm not wrong, or 2. But yeah, it worked flawlessly. Okay, but as you might be wondering, okay, but only Whisky was, only this cat was in all the area. There were no more distractions. Yeah, it was a simple demo, but there's more coming later. and now we found any cat. If there was I don't know, another cat here, it would have detected that one. We're not detecting cats, specific cats yet, and for that we have to train our classifier. You have to meet the other cats, and yeah, this is going to become more interesting. Let's see. Well, it's time for the last component of the project, the cat classifier. Okay, so first let's meet the cats. Okay, first we have Whisky. You already know him. It's a toy cat, the one that helps us the most in the project. Then we have Juana. It's a real cat. Yes, she has only one eye. We adopted her as with this condition, but now she's very happy. Then we have Lily. This is another cat. She loves to sleep. Well, every cat loves to sleep. And finally we have Yayo. Yayo is also a toy cat. It's a replica. He was the last to enter in the equation, well, for some reasons. And yeah, he's a replica, but unfortunately he's very small, so he's smaller than a cell phone. Okay, and these are the cats, so we are going to train our classifier for these 4 cats. So the idea is we are going to, well, the idea of the project is that you will record a video of your cat, and then the drone has to find it. Okay, so in this case we are going to record videos for these 4 cats. They can be pictures as well, and yeah, based on that the drone will find them. So we are going to have these 4 categories. In reality, when implementing this in real life, we would have one more category that would be the rest of the cats. Okay, but well, for the scope of this project, we are not going to do that. Well, yeah, the other category would need well, a considerably big data set of the rest of different cats that are not this, and I am lazy to get data sets. That's one of the reasons I chose this, is because generating a data set based on videos is kind of easy. You just record the cats in different positions, different places, doing different things, and then you have many frames that become your data set. So okay, so for the project scope we are going to have these 4 cats, and well, and don't forget that the reason is because we want to find a specific cat, right? I don't want the drone to find any cat, and then in the first cat it says okay, I'm done. No, we want to search for a specific cat. For example, if you want to search Lily, we would, well, first we would train and we'll do all that, and once everything is trained, when running the program, I could say, okay, drone finder, please find Lily, and it will do it. Okay, yep, these are the. Okay, now we are going to create the data set based on a video. So this is going to be for Lily. So here I have the video. It's the one we are going to use. Okay, we are filming her in doing her cat life. Okay. Okay. So what we're going to do is we're going to check each frame, and then run the cat detector and crop the image of the cat on each frame, and then save each image. We are doing the following. With 60% probability, this is going to go to the train folder. Here I have it inside dataset, valid, train, and test. So with 60% probability, this will go here in Lily, train Lily, with 20% probability to valid Lily, and with the other 20 with test Lily. Okay. Okay, let's run it. It's running, and we'll see a preview of the progress. Okay, here we can see it's checking each frame and cropping the cat detections. And each one of these rectangles will become an image file in the folders we mentioned. Okay, it's done. And now we can see here inside Lily, for example, in train, we have all the images. Okay, let me show you. For example, here they are. Okay, and that's it. That's how we generate our dataset from cat videos. Well, now we have our dataset ready for the 4 cats, and it's time to train our network. Okay, first, well, we are going to use a ResNet 50 classifier. Okay, well, I won't explain this structure. Let's skip it. Okay, and this is a very simplified version of it. So, well, this is ResNet 50, and well, the input is an image, and it has many layers here. Well, it's very simplified. Then before the last layer, there are 2048 outputs, okay, that feed the last layer. And this layer is called FC in PyTorch. Okay, and then well, the final result of the model is to have 1000 outputs, which are the categories that this image might belong. Okay, but in our case, we don't want 1000 outputs, right? We would just want 4 outputs for the 4 cats we have. So traditionally, as well as in the course, you would replace this layer with your own layer, right? And then have 4 outputs. But that has some issues. Well, at least for this project. Well, one is that if you do that, you have all the monolithic model, and it's in a single unit. But in my case, I want to use Raspberry Pis for classifying, and they are, as you know, they are limited. Their computation and all that is very limited. So running a full ResNet model as well, sending them in a federated way, would be too heavy for them. Okay, so so I had an idea to accomplish this, which is I am deviating a little from traditional transfer learning, and I am doing the following. I will replace this SV layer by an identity layer. Okay, let me show you. Okay, and this identity will, whatever comes in will go out. Okay, so the 2048 outputs will come here and will be they will be the output of the model. And then I'm going to use my model, my classifier, as an independent component. So not replacing as in transfer learning, but adding it as a different model. So here we would have the 4 outputs. Well, I forgot to put them here, but so that in this way we have them decoupled. So this has great benefits. One is that we can train all these with CUDA and this with the Raspberry Pis, because it will be an independent model that will get 48 inputs and 4 outputs. It's just a tensor instead of an image, much simpler. And these can go to the Raspberry Pis in a federated way. Okay, so this will be trained by the Raspberry Pis as an independent model, and the ResNet will be done locally with CUDA or with your CPU. So because well, this is an already trained model, so there's you can benefit of CUDA and all that, and do all this locally and have this federated in a federated way, so that it won't hurt performance, right? So this is the mechanism I designed, and I'm very happy with it because the performance was great in my opinion. Okay, now let me show you how we train the model and use the Raspberry Pis and all that.
Here we have our 2 Raspberry Pis. They are Raspberry Pis Model B. They are the exact same model, fortunately. So I was able to install PyTorch, which, by the way, it was so painful to compile PyTorch 1.1 and install all the dependencies and all that, PyShift and all that. And so I cloned the SD card to this, first creating an image, which, by the way, I uploaded to the cloud if anyone else wants to try it. And okay, so it's cloned and it worked like a charm in both. And these are connected by Ethernet to the network and my PC. Yes, now these are going to train the model in a federated way. And one more thing is they have very original names. This is Raspberry 1 and Raspberry 2. Okay, now let's see how we train the model with them.
Okay, as we saw in the generating dataset section, we have here in the dataset folder 4 subfolders: test, train, and valid. Sorry, 3. And each one of these has one subfolder for each cat: Juana, Lily, Whisky, and Yayo. Okay, and here are the images for each cat. Okay, now let's run the training notebook. Okay, first, nothing remarkable, the imports. Okay, so the transforms. Okay, I'm here loading the train and valid and test folders with image folder datasets, and okay, and it creates these 4 categories: 0 Juana, 1 Lily, 2 Whisky, and 3 Yayo. Okay, then okay, trivial stuff. Okay, here. Okay, this is important. We are loading a ResNet 50 pre-trained model, and we are storing it two versions, one with CPU 1 and a CUDA 1, if available, of course. And this WLL stands for without last layer, so it's ResNet 50 without last layer. Yes, you guessed it, it's because we are going to do transfer learning, but in a special way. Okay, I will run it. Okay, then here, this is also important. After loading the ResNet model and sending one to CUDA, then we are hooking to PyShift. This has a reason. PyShift has a bug, which I discovered with blood, that once you started hooking, you cannot send a model to CUDA. You get exceptions. So yeah, I suffered this and found the solution by experimenting. So that's why the hooking is here. Okay, let's execute the hook, and here we have the, okay, some warnings we don't care about. And here we have the connections to the Raspberry. Okay, here we have Raspberry 1, which is IP48, and Raspberry 2, IP49, and they are called Raspberry 1 or Raspberry 2. Very creative. Okay, and here I have them in the two remote consoles. So I'm going to start. This is the Raspberry 1. I'm going to the IP48. I'm going to start it with the verbose option so we can see what's happening, and enter, and also for the second one. Okay, IP49, yes, verbose. Okay. Okay, great. So, okay, so they are running, and we're connecting to them. Oh, it looks they didn't start yet. Let's see if they are ready. Okay, serving. Okay. Okay, that was fast. Okay. Okay, this is very important, not related to the Raspberry Pis. But so for the ResNet, we with the mechanism we are going to use that you already explained, we are going to freeze. Sorry, we're going to use all the ResNet model without the last layer, but we do care about the output of the previous layer, not the previous one to the last one. So we are overwriting the last layer with an identity layer. This is basically returning whatever it gets as parameter, and so that when we run ResNet now, it won't give us the usual output, but it will give us the output from the previous layer to the last one. Okay, to the layer before the last one. And this is going to be crucial for our performance because we are going to run ResNet in the PC with which has CUDA enabled. So we do, then we are going to use the other model, the actual classifier, in a federated way. So we are going to send just the classifier to the Raspberry Pis, and not the full model that is ResNet plus classifier. Okay, so this split is crucial for the performance. If not, we are going to be running the Raspberry Pis for days, or well, hours or days. I don't know. Okay, okay. So we have this ResNet 50 now. WLL actually makes sense without last layer. Identity. Okay, and then we freeze the gradients. Okay, now some debugging with CUDA. Okay, and here I'm doing what I just explained. This model LL will be, well, LL stands for last layer, and this is the classifier. Okay, this is the actual classifier. So it as in transfer learning, it has the same structure as the ResNet last layer, but notice that I am not attaching this to ResNet. This is independent. Okay, and this is the model that I'm going to send in a federated way to the Raspberry Pis, so that this is a very small model, so it will run fast instead of sending all the full model with ResNet. Okay. Okay, so, and I am setting the request right as true, because this is going to learn. Okay, then we have the more trivial stuff of learning. Okay, we have our train and validate method, and here the important part is this. Okay, so as we said, we are going to use ResNet with CUDA to calculate the output before the last layer. Okay, so I'm creating this variable rwll outputs, and this will be the output of the ResNet without the last layer. Okay, so we are sending the inputs to CUDA if available, and then this is passing to ResNet, and in the last layer it will go to the identity one. That's crucial. And then well, getting a CPU so we can send them so the outputs are in the CPU, so we can send them to in a federated way. Okay, then we have the worker. So we are setting it as Raspberry 1 for pairs, for pair batches, and Raspberry 2 for odd batches. Okay, even on odd, sorry. Okay, and here we are sending the outputs from the ResNet without the last layer to the worker. Okay, Raspberry 1 or 2. And here, this is also crucial, we are sending the model-less layer to the worker, but this is just the classifier, not the full model. It's independent. Okay, and in the outputs, okay, now this we have the real outputs. Okay, so the outputs will be the result of the classifier. So it's split in two. To get the actual output, we first run the ResNet, and the output of ResNet will become the input for the classifier. Okay, so we have 2048 outputs. It's a tensor of 2048 numbers, and this is going to pass as input to the classifier. As you can see here in the classifier, it has 2048 inputs. Okay, so we have the output. ResNet is working locally with CUDA, and the models are being sent to the Raspberry Pis. Okay, then we also send the labels to do further calculations. Okay, it's learning in the training in the Raspberry Pis, and then we get the model back, and so forth. And then we have all these trivial stuff for calculating accuracy and all that. And for validation, we have something similar, but we don't need to send to the Raspberry Pis because it's a different data set, and this is doing everything locally, and but it's the same criteria. It's split into steps. First ResNet and then the classifier. Okay, and yeah, all this trivial stuff. Let's run it. And oh, sorry, one thing I was forgetting is that we are here to the end. We are saving the model so that after choosing the right one based on the charts, well, we can load them from disk. Okay, and I was running just a definition. I'm not triggering the train. Okay, and now let's trigger the training with 20 epochs. Okay, epoch 1, and let's see the Raspberry Pis. Okay, yep, as you see, we are seeing everything that is arriving to the Raspberry Pis via WebSockets, and this is going to take a while, I think, but not much thanks to the split we did. Okay, so training has finished. It didn't take that much. I don't know, around maybe 40 minutes, something like that, a little more maybe. Okay, and let's see the output of the Raspberry Pis. Okay, yeah, it seems it's not cleared. Okay, but no problem. It finished, and looks we have very good results. Okay, let's plot. Okay, I like this. Okay, here we have our training loss, validation loss. I think maybe a good fit could be here or here. Okay, we'll see. Okay, and now let's plot the accuracy. Oh, what happened? Okay, here it's very good accuracy. Okay, now we are going to run some methods to test accuracy and prediction. Okay. Okay, let's see with I don't know, epoch 8. Okay, and let's evaluate the model with a specific example. Let's use the prediction. Okay. Okay, it's taking a random image from the test set. And okay, here we go. Okay, this is clearly Yayo, and let's see prediction Yayo. That's very good. Expected Yayo. Okay, let's run one more. Okay, Lily, expected Lily. Okay, this is working very good. Okay, and now here we have some measurements about the time it takes, but there's one thing here. For example, it took, I don't know, half a second, but we are using, due to the bug I showed, but we cannot move to CUDA, so we are using the CPU models. So this with CUDA will be much lower. So to get accurate times, we should run this in a separate notebook without PySift, so we can use CUDA. That it will be used actually when we are running the drone. And yeah, that was it. This was the training, and I hope you enjoyed it. Here more test about the accuracy. I hope you liked it. Okay, there's still a lot to do in the project, so let's continue. All right, now we have our classifier trained, and now in the code we are going to join it with the detector we did initially, and this combination will be called my cat detection model. So basically, well, the drone will get a frame as input from the camera. It will send it to the model, and it will get an array of a list of detections of all the cats he found, but only from the 4 we have, right? So based on that, let's say it says, okay, I found Lily in this coordinate, and well, we will see in the program if we are interested in Lily, or maybe we want to search, I don't know, Whisky, and based on that we can decide to ignore a cat or to consider it as found. Okay, now we are going to do we are going to try to do a demo with real cats, Lily and Juani, and I'm saying trying because, spoiler alert, it wasn't possible because they, okay, I'll say it, they freak out. The drone is too noisy, too noisy, and the cats freak out with it. This wouldn't happen with a professional drone. Let's say if this project goes to real life, because a professional drone would fly very high, and well, so then the noise wouldn't be a problem. But in this case, we are with low height, and so it freaks the cats. Okay, do you want to see that? Okay, let's see. This will be fun.
No, creo que... Ay, Mona, perdón.
No te preocupes, ya está. Ay, ahora. No, no, ya está.
Yeah.
So that was fun. So as you saw, it's not possible to do it with real cats with this drone in particular. But I didn't want to give up. So what I did is, well, to test the classifier in the following demo. Well, I ran the program in debug mode, which means, well, maybe I don't know if the name is the best, but it means that the drone motors will be turned off, but the camera and AI and all that will still work the same. So given it's too noisy, I will have to hold the drone with a selfie stick, and I will move the drone instead of the motors. So the autonomous flying of the drone, that component will be ignored. Well, that won't be working, but the AI, the classifier and the detection, they should work, and hopefully should detect clearly. I wanted to do this because I wanted to work with real cats. This has to detect real cats. It's not the same to detect a toy that is rigid and static. So well, I know the drone will be with the motors turned off, but I want to see if it actually detects and classifies a cat, if it recognizes Lily. So in the following demo, we are going to put Whisky. He has to be ignored. He will be ignored in the middle, and to the end we will have Lily, and hopefully she will be detected, and well, the motors, the drone motors will be turned off, so for you to be aware. Okay, okay, let's do it. Okay, so the demo was successful. Well, the drone was quiet, but it was able to ignore Whisky, and then it detected Lily, so it works with real cats. I'm so happy. So as one more proof of this, let me show you a small video that was processed with our detector and classifier, and it shows that it detects all the cats. Okay, so the time has come for the final demo, where we are going to put everything together, all the effort, all the everything that was programmed, all will be shown in this demo. Okay, so in this last demo, we are going to have well, all this area delimited by the squares. We are going to have many objects, because so far we didn't have distracting objects. and that's important because in real life we are going to have tons of objects and different things, so it has to work with that. Okay, so the drone will go by here sequentially. It will find Yayo, and now I modified the program to show a rectangle when he finds someone, but he will be ignored because the target will be Whisky. We want to find Whisky, so Yayo will be found but ignored, and then it will keep going, and it has to ignore all the objects, and then it will find hopefully Whisky. And there's one more thing we didn't show. We said initially that we want to align with the cat, which is basically the same as following, right? So once he finds the Whisky, we're going to pull him, and the drone has to follow. So follow it. Okay. Okay. Let's go.
So fortunately, the cat detector and the cat classifier are working with real cats, as we saw with Lily. That was great, but unfortunately we couldn't search her with the drone, and so now we are going to put everything together. Okay, what we are going to do is the drone will search for Whisky that is there. Okay, but in the middle we will have Yayo. He has to be ignored. Now I changed the program so that we can see a rectangle to show that he's detected. So this will be more clear that he was detected but ignored. And well, the drone will hopefully go by there. He will ignore Yayo, and then hopefully he will find Whisky that is here. And one more thing is that in reality we don't only want to detect the cat, but also to follow it, right? Or to, we could say, to align with it. In real life with a real drone, if we are, I don't know, in 50 meters high, we don't want just to say, oh, okay, I found a cat. We want to align to it, which is basically the same as following. So let's hope it works. Once he found Whisky, I will pull him, and the drone has to follow him. Okay, this is an ambitious goal, and let's hope it works. And I also put many objects that shouldn't be detected, right? A pot, a ball, a house, a toy house, a car. Well, many things. Okay, let's hope it works. I am very nervous. This is the last experiment, the one that joins everything. Let's do it. Okay, let's see. Good luck, drone. He found Yayo. He found Yayo. He's ignoring it. Yeah. Don't go out. Don't go out. Yeah, drone. Yeah. Let's go, drone. Yeah. He almost went out. Almost. Vamos. Vamos, yeah! Great! Let's go! Let's go, let's go. Yeah, that's the time. That's the time. Please, please, please. Please. Find whiskey, please. Find whiskey. Find whiskey. Yes! He found it! He found it! Yeah! Awesome! Awesome! Yeah! He follows him. Yeah! He follows him. Awesome! Yeah! Yeah! Yeah!
Okay, the demo worked great. It worked very well. Well, some conclusions. Well, there were some, if you put attention, there were some frames where Yayu was detected and he wasn't supposed to be detected. And yeah, and analyzing this, this is well, some reasons could be that one is that when we were defining the data set, when defining the testing and validation data sets, we were using closed frames. So so closed frames, if there's no movement, they are kind of the same. So that could cause false sense of accuracy. That's one thing, and other is well, it seems I didn't use the model for the right epoch that we selected. Okay, but doesn't matter. In general terms, this idea works, and I'm very happy. And this can, as we said initially, this can be easily extended to other fields, like, I don't know, rescuing people, yeah, detecting person, detecting any kind of object, and the drones should find it. And yeah, and it doesn't have to find only one target. It can find many and send pictures to your phone, and with GPS to give you the coordinates and all that. So so yeah, this showed how hard it can be to do a real project, because in theory this was easy, but in practice it was really hard. And well, when applying this in real life, we wouldn't have many of the limitations especially for the drone. So we wouldn't need those squares to limit something, because we would have a GPS and yeah, so but we would have other kind of issues, right? For example, I don't know, not crashing with power lines, and yeah, it would be a different problem, but with the same core idea. So this, we were able to use federated learning that was learned in the course. We were able to train remotely in Raspberry Pis. We did detection, object detection, also custom detection without deep learning for the squares, and also classifying using neural networks, training a model, checking the accuracy and all that. So I hope you enjoyed it as much as I did. I love the project, and for sure there's still a lot to do. And okay, thank you.